Today, I will present our paper titled Learning to Navigate Intersections with Unsupervised Driver Trait Inference. I will begin with an introduction. Navigation in uncontrolled intersections, such as the one in the figure, is challenging to autonomous vehicles. Because first, the internal states of other traffic agents are not fully observable to the ego car. And second, traffic lights and stop signs are not present to regulate the behaviors of traffic agents. Therefore, they implicitly interact and negotiate with each other, making their behaviors complex. To successfully complete the navigation task, the ego car must infer the traits of other drivers, such as their driving styles, and adjust its driving strategies accordingly. Some previous work only encodes the short-term information, such as velocities and accelerations of drivers, but they ignore the persistent properties, such as traits. Another work uses supervised learning to classify the traits with labeled data, but the labels are hard to obtain and usually don't exist. To address these problems, we propose a novel unsupervised approach to learn a representation of driver traits with a recurrent variational autoencoder network. Then we use the trait representation to improve the navigation of an autonomous vehicle through an uncontrolled T-intersection in simulation. Our method exhibits promising results and outperforms previous works. To learn a representation of driver traits, we assume that the drivers are either conservative or aggressive. Conservative drivers have lower speeds and maintain larger front gaps. The conservative drivers yield to the ego car if the ego car intercepts in front of them. Aggressive drivers, however, have higher speeds and smaller front gaps, and they will not yield to the ego car. We collect and preprocess a dataset of driving trajectories from the simulator. Then we first use an RNN to encode the trajectories to a latent representation space. And then we reconstruct the trajectories with another RNN decoder. We train the network by optimizing the evidence lower bound as shown in the equation. The right figure visualizes the latent representation that separates the conservative and aggressive trajectories. To learn a navigation policy, we model the T-intersection scenario as a POM MDP. The observable states are the positions and velocities of all cars in the scene. The traits of other drivers are the hidden states and are inferred by the trained encoder in the previous step. The output actions are the longitudinal velocities of the ego car. Our policy network is a GRU, and we use an attention module to assign weights to each observed driver. The policy network is trained with model-free RL. After training, the ego car is able to successfully merge into the upper lane by yielding to the aggressive drivers and intercepting in front of conservative drivers in most cases. More quantitative results can be found in the paper. However, our work has the following limitations. First, the driver trajectories are generated by a rule-based policy. In future work, validating our approach with real driving datasets is needed. Second, it would be interesting to generalize from binary traits to more sophisticated traits. Thank you for listening.